We're going to talk about how to describe lines and then after that planes in three-dimensional space. First, we'll ask ourselves the question, how do we describe a line? And even though our goal is to describe a line in three-dimensional space, let's start with talking about lines in the plane. So let's say here's our standard XY plane. How do we talk about just some general line? Well, let's say I want to describe to somebody this line. Well, there are many different ways you could do it. One thing you all know from geometry is that if you give me 2 points on the line, then in fact there's a unique line that goes through those 2 points. So I should say if you give me any 2 different points in the plane, there's a unique line that goes through them. That's good, so that 2 points, you just tell me 2 points, that should describe the line, but it's not the most immediately useful description of a line. So let's talk about other ways to describe a line. Let's say you tell me 1 point on the line. I could use one of those, but I'll just use a different one. Say this point on the line. And you also tell me the slope of the line. Say slope m for the line. And let's say that this point is the point x naught, y naught. Is it easy to describe a line which contains this point x naught, y naught, and has slope m? Well, yes, you all know how to write what we call the point slope form of a line. A line containing this point with slope m has equation y minus y naught is equal to m times x minus x naught. Now you could write this in many different forms, but for us we'll just leave it like that and say this equation will be the equation for the line, and that means that the set of points on the line is exactly the set of points xy, which make this equation true. That's a very useful way to talk about the line because we can find points on it very easily, and we can easily test the point to see whether it's on that line. Can we do a similar thing for lines in three-dimensional space? And at first the problem looks much trickier. We have our three-dimensional space, here are the standard coordinate axes. And somebody just has a line going through that, a line perfectly straight, as you can see, a line going through space. And we want to know, how can we describe the line? Well, let's say that I try to follow this model and tell you, here's a point on the line. Say that that point is the point x naught, y naught, z naught. Is there some equivalent of this idea of a slope that we can use? Well, things are a bit trickier, and it's very hard for me to draw this. I might try like this. There are lots of different lines in space that go through that point. And it's not just about having different slopes. You can imagine, if you picture this in three-dimensional space, there are many, many, many different ways you can have different lines that go through this exact same point. And what will distinguish our original line, the one that was drawn in black here, from all the other lines? There's not just going to be one number, the slope, that will do that. But it turns out it's very easy to describe our line if you can tell me a vector, and I'll use blue for that, if you can tell me a vector that specifies the direction of the line. So this blue thing I've drawn is a vector, I'll call it V. And if you know the point x naught, y naught, z naught is on the line, and you know this vector, we're going to call this the direction vector of the line, that goes in the direction of the line. And we could go either downwards here, or upwards, any vector that lies entirely in the line. And when I say lies entirely in the line, that means if you place the beginning point of the vector on the line, then the end point, the tip of the vector, will also be on the line. So that means this entire arrow or vector lies in the line. That should now specify exactly what line you're talking about. So we get this idea that a line can be specified by a single point along with a vector. This gives us the idea of writing the vector equation for a line. Here R naught And notice these are boldface, R, R naught, and V. These are vectors. R naught will be the vector, X naught, Y naught, Z naught. We're going to use a vector to denote our initial point on the line. Let me redraw our coordinate axes here. When I said this was the point X naught, Y naught, Z naught, I can specify that point by giving you this vector R naught, which you can think of as a vector from the origin to that point. But really, we're just thinking of the coordinates of that tip when I write this vector R naught and say this is a vector on the line, meaning the tip of the vector, when the tail is there on at the origin, the tip of the vector is on our line. And remember, this vector V, I'll say the vector V, I'll just give it coordinates A, B, C, whatever the coordinates are for V. Here's our vector V. That's our direction vector for the line. Our line will consist of all points on the line containing this point, specified by the vector R naught, and in this direction V. Now, what does it mean, all points then on the line? Well, it means from this point I can add V. I can take the vector R and add V to get to this other point. I could add 2V or 3V or a half V. I get all these points just by adding a multiple of V. If I take a negative multiple of V, I'm going in this opposite direction, like this. So if I start at this point specified by the vector R naught and add any arbitrary multiple of V, I get all these other points on the line. And that's why we say for our line is specified by R, which will be the vector X, Y, Z. Think of an arbitrary point on the line with coordinates X, Y, Z can be written as R naught, which is X naught, Y naught, Z naught, plus some number T times our vector V. Here, T is any real number. And so when I put that all together, I'll write it as X, Y, Z equals X naught, Y naught, Z naught, that's R naught, plus T times A, B, C. Now, to get what we call parametric form of the line, I'll just combine this thing on the right, these two vectors R naught and T times V naught, as X naught plus TA. If I look at the first component, here is T times A, and I add that to the first component here, X naught. Let me rewrite that, T times A. The second component is Y naught plus T times B. The third component is Z naught plus T times C. This is R naught plus TV. And I need X, Y, Z to equal this vector. In other words, component-wise, X has to equal X naught plus TA. Y has to equal Y naught plus TB. And Z has to equal Z naught plus TC. We call this the parametric form of the line because here T is just any number on the whole real line. And you pick any number T, you plug that in, think of T as your parameter, just the way we were talking about parametric curves at the beginning of the quarter. T is any value for your parameter, and whatever value for T you pick, you get a point on the line, X, Y, Z. We can think of that as a vector R lying on the line. So here's our vector R lying on the line, meaning the tip lies on the line if here's R naught. And R here would just be R naught plus 1 times V. Here would be a vector which is R naught plus, say, negative 3/2 times V. Here you'd have something like R naught minus 2 1/4 times V, things like that. And that would lead to different points X, Y, Z on your curve. Now there's another way people can talk about a line. We can create what are called the symmetric equations. In general, those start by solving for T in each of these equations. In the first equation, when I solve for T, I get T equals X minus X naught divided by A. If I solve for T in the second equation, I get T as Y minus Y naught over B. And in the third equation, if I solve for T, I get C minus Z naught over C. So there's one important condition here. This is as long as a, b, and c are all non-zero, then this is what we call the symmetric equations for the line. X minus x naught equals over a equals y minus y naught over b equals z minus z naught over c. Notice that this system of equations is really two equations. It's this equals this, and this equals this. And if you have those two equations, of course, you'll get this first one equals the third one as a freebie. But really, this consists of two linear equations in the three unknowns. A single linear equation will not be enough to specify the line. It was in two-dimensional space, just a single linear equation. We use the term linear equation to denote an equation that specifies a line in two-dimensional space. But now we have two linear equations in our three variables, x, y, and z, which together specify the line. We'll see examples of that shortly. Now, I say that's what we do if a, b, and c are non-zero because it only made sense to solve for t as long as in the first equation if a was non-zero, in the second equation if b was non-zero, and in the third equation if c is non-zero. We're going to see in the examples coming up what to do if any of these coefficients are zero, and I think that will be made clear shortly.